right? So in case of two-dimensional flow, so sources and sinks is one concept. And in fact, this is one of the very important concepts. Right? So here, in the case of two-dimensional flow, so if W is the complex potential, then W can be written as phi plus I psi, where W is the complex potential and phi is the potential function. And psi is the stream function. And both potential and stream function functions are always mutually perpendicular. Mutually perpendicular. So this is the basic rule, right? So in this basic rule, suppose if you have the equipotential lines like this, so these are the equipotential lines. So equipotential lines, we mean there will be a definite associated potential at every point on this line, but everywhere it is equal. But this is having a different potential magnitude here, but everywhere on this line it is exactly the same. So these lines we call as the equipotential line. So these lines are called the equipotential lines. Now, so as and when there is a flow, so whether it may be like gravitational field, or whether it may be a fluid field, or it may be an electric field, the flow will be always perpendicular to the equipotential lines. So here in this case, fluid flow will be exactly perpendicular to the equipotential lines. So these lines, the lines which contains the equipotential, are also called as equipotential plane also, because usually it won't be lines, it will be a surface. So that's why this is what we call as the equipotential surface. To represent on the graph, we call it as lines. Now if you take an electric field, so there is a charge inside. Imagine there is a ball around it. That ball is nothing but the equipotential surface, because at every point on the surface, the potential magnitude will be exactly same. Now here also, when there is a fluid flow that is happening towards this direction, whatever may be the kind of shape this surface contains, these are equipotential surfaces. Now exactly perpendicular to that, so the flow will be happening. So this is everywhere, the condition is it has to be 90 degrees. So this gives an excellent analysis in case of complex analysis. Now if these lines are nothing but, so if equipotential lines are nothing but the potential function phi, so it may be a function of x comma y comma z, or it may be a function of time also. And then these are nothing but the stream lines. So stream lines are x comma y comma z comma t. So this is called the stream function. And this is called the potential function. So these two together always comes in pair, and this pair is represented with W is equal to phi plus I psi. So this is the fundamental principle in the entire analysis of sources and sinks and the two-dimensional flow in case of fluids, right? So not only for the fluids, the same analysis is applicable for wherever there is a potential field. So that potential may be electric potential, or so gravitational potential, or it may be a fluid potential. It is exactly the same analysis. That's what we are going to do in case of any physics problems that we are going to deal with the fields, right? So this is what we call as the complex potential. So this is what we call as the complex potential. Now, till now whatever we have discussed is not related to phi or psi. So we are dealing with only the velocity. Now the velocity components are nothing but q is equal to ui plus vj. So this ui plus vj, we have ignored the next component, that is the k component, because we are dealing with two-dimensional flow. So this we are dealing with the two-dimensional flow, and for a conservative field or for a potential field or potential flow, this velocity can be written as minus del phi. So minus del phi is nothing but minus dou phi by dou x plus I times j times minus dou phi by dou y. So which essentially means that here u is equal to minus dou phi by dou x. So u is equal to minus dou phi by dou x and v is equal to minus dou phi by dou y. Now these are the components of the velocities along x direction and along y direction. Now here in case of complex potential, right, so this phi and I psi is there. Now here what we have got is u is equal to minus dou phi by dou x and v is equal to minus dou phi by dou y. And along with these relations in case of complex analysis, what we have something called the CR equations, Cauchy-Riemann equations. So this CR equations, what it says in case of complex analysis is dou phi by dou x is equal to dou psi by dou y and dou phi by dou y is equal to minus dou psi by dou x. So here from these three different sets, so one is the fluid velocity related equations, and another is the Cauchy-Riemann equations, and another is the complex potential equation. Now these three together will frame the complete analysis of two-dimensional fluid flow. Got it? So here the way you can relate here it is, so phi is there here. Now if I take dw by dz, this is what we call as the complex velocity. That means z is a complex number and w is a complex function. Now the derivative of this with respect to z is nothing but the complex velocity. This complexity velocity is nothing but dou phi by dou x plus I times of dou psi by dou x. So this is the complex velocity. So how we got this? This is the derivative of an analytic function in case of complex analysis. This is what we are going to get it here. Now dou phi by dou x is nothing but the velocity component along u. So velocity component along x direction. And then dou psi by dou x you can replace with minus of dou phi by dou y with the help of Cauchy-Riemann equations. So this can be written as dou phi by dou x plus, so dou psi by dou x can be written as minus dou phi by dou y. So this is dw by dz. So this dw by dz is nothing but the complex velocity. So this complex velocity dou phi by dou x you can replace with minus u, and dou phi by dou y you can replace with minus v. So this is minus u plus I times of v. So this is what we call as the complex velocity. So what we are trying to target in the whatever may be the two-dimensional flow analysis, whether there is a presence of source or whether there is a presence of sink or whether it is a simple potential flow, in all the cases whatever we are going to take care is, first we will identify the complex potential. Once we identify the complex potential, you will try to find out the velocity by just taking the derivative with respect to z. So this is what you are going to relate to minus u plus iv. So here some cases in the problems, right, what they are going to ask is, mostly they will be asking us to find out this stream function, right? So this stream function you may get the potential function. So with the help of potential function you will be able to identify the stream function. That's what is needed. And one step ahead of that is, in case of presence of sources and sinks, what we are going to get it is, we will try to model a source as a complex potential and we will try to model a sink as a complex potential, and that complex potentials we will add it up together, all the effects of all the sources and sinks together as a simple single complex potential. That simple single complex potential, once you find it out, from that function you will be identifying the separate parts, the real part and imaginary part, real part will be the complex potential. So real part will be the potential, or this is a scalar potential, and psi will be the stream function. So these two you will be identifying separately. Got it or not? So this is the complete analysis of the two-dimensional flow. That's what we are going to deal with. Got it? Any questions on this? Any questions? Okay, great. So this is very, very important discussion for this entire topic. You just note down each and every aspect in it. So if you know the potential, so you have written, so the CR equations are dou phi by dou x is equal to dou psi by dou y, and dou psi by dou x is equal to minus dou phi by dou y, right? So here these are the CR equations, and then what we have got, the velocity as dw by dz is equal to minus, so dou phi by dou x plus I times of dou psi by dou x. Now, if you know the stream function rather than the potential function, the same thing you can replace with. So this is dou phi by dou x can be replaced with dou psi by dou y plus I times of dou psi by dou x. So this is dw by dz equivalent. So this is what is nothing but the velocity expression if you know the stream function. Got it? And then if you know the potential function, the same thing can be written as dw by dz is equal to dou phi by dou x plus I times of dou psi by dou x can be written as minus of I times of dou phi by dou y. So this is the complex potential. From the complex potential, right? So you will be deriving the potential function, or if you know the potential function, you will be able to derive the complex velocity. Got it? So this is if you know psi. This is if you know phi. Got it? Okay. So note down one problem based on this understanding. Show that u is equal to u is equal to 2axy, v is equal to a into a square plus x square minus y square are the velocity components of a possible fluid motion, or the velocity components of a possible fluid motion. Possible fluid motion. Determine the stream function. Determine the stream function. Can you solve this? This you might have already done in complex analysis. So velocity components are given, but in complex analysis usually either phi or psi will be given. So here to find out the stream function, so there actually in the complex analysis we have given the phi value, that is the scalar potential value. But rather than that, he has given us the velocity components, and you know the relation between the velocity component and the potential, so scalar potential. From there you can derive this. Yeah, minus u plus iv is the complex potential, sorry, complex velocity. First, you need to verify whether it is a possible liquid motion or not. For that, what you need to do, you have to verify the continuity equation. So del dot velocity, so del dot q should be equal to 0, and you have to verify that. Then only this is a possible liquid motion. Otherwise, this is meaningless. Anybody got the answer for this? Anybody got it? Okay, so let me solve this. See this here. First, we will verify the continuity equation if it is satisfied or not. So del dot q is equal to 0. That means dou phi by, so del dot q is nothing but dou u by dou x plus dou u by dou y. I dou by dou x plus j dou by dou y dot product with ui plus vj. Now dou u by dou x plus dou v by dou y is equal to 0. So this is the continuity equation, and for that function dou u by dou x will be 2ay, then so dou v by dou y is nothing but minus 2ay. So this is equated to 0. Hence del dot q is equal to 0. So therefore the continuity equation is satisfied. Is satisfied. Hence it is a possible liquid motion. So it's a possible liquid motion. Now the velocity components. So here u is equal to minus dou phi by dou x, and v is equal to minus dou phi by dou y. So this is the velocity. Now he is asking us to find out the stream function after giving this velocity components. And in the counter way, we have the CR equations are dou phi by dou x is equal to dou psi by dou y, and dou phi by dou y is equal to minus of dou psi by dou x. Right? So these are the CR equations. Now from the CR equations, you can find out the velocity components. So minus of, instead of phi, I am going to use psi. So dou phi by dou x, I can equate to dou psi by dou y, and then v I can equate to minus of dou phi by dou y can be written as dou psi by dou x. So once you get this, then equate the value of u here, that is 2a xy is equal to minus dou psi by dou y. And similarly, v can be equated to a into, I think this is capital A. Yeah. So capital A into a square plus x square minus y square is equal to dou psi by dou x. So these are the two important relations which you can make use to find out the stream function psi. So both the equations we have got. So Lizu, I think so you have got this, right? I have clearly explained here. You check this. Fine. So here dou psi by dou y. So I can find out minus dou psi by dou y, or minus dou psi is equal to 2a xy into dou y. Now if you integrate on either sides, psi is equal to minus of, I'll take this minus to the other side. So minus of 2a y square by 2 plus some arbitrary function of, so you are doing the integration with respect to x, so hence it may be a function of x comma t. So here this 2 will cancel, so psi is equal to minus a y square plus f of x comma t. So this is the function psi, but there is an arbitrary function that got involved here. So this is an arbitrary function which is independent of y. So because you are doing the integration partially with respect to y, right? So that's why you will get any arbitrary constant, maybe a plain constant, or maybe a function of x, or maybe a function of t, or maybe a function of both x comma t and with plain constant, right? So we don't know what is the kind of scenario what we are going to get it here. This will be decided based on the initial conditions, right? So this you can find it out even with this relation also. We have the other relation, dou psi by dou x. So here the left side part is a into a square plus x square minus y square. Now the right side part, you know the function psi, so you can just do the derivative. So this is minus a. So with respect to x, so this part will become 0 plus f can be written as dou f by dou x. Got it? So dou f by dou x can be equated to this one. Now here, so psi is nothing but a square plus a square x, so a x square minus a y square, and this is equal to dou f by dou x. Got it? So that actually you need to integrate it. Just note down this. I'm going to erase it and rewrite it. Yeah, I think so. You are correct. So we missed the x here. Yeah. Then actually this part is going to be changed, right? Yeah. Anyway, you note down till this point. I'm going to do it from there. Got it? So from this, so this value, that is a into a square plus x square minus y square is equal to dou psi by dou x, where psi is minus ax y square plus f of x comma t. So then this will be minus a y square plus dou f by dou x. Dou f by dou x. Now this is equal to a square plus x square minus a y square. Now if you correlate the corresponding terms, dou f by dou x can be equated to a into a square plus x square. So this is dou f by dou x. Then if you want to find out f, then this can be integrated with dou x. So this you can integrate it. So this is a into a square into x plus a into x cube by 3 plus some random function of e alone. So this is the function f. Got it? So once you got this value, you can replace with the original function. So psi equal to minus axy square plus a square x plus ax cube by 3 plus g of t. So this is the function, stream function. If it is independent of time, then g of t will be a plain constant, which can be found with the initial conditions. Got it? I hope everybody got right. So this is simply with the help of complex analysis, we are trying to find out the stream function. So, but the potential function was given in terms of velocity components. That's the only difference. Indirectly, the potential is given and we found the stream function. Note down one more. A velocity field is given by Q equal to minus xi plus y plus t into j. Find the stream function and the streamlines for this field at t equal to 2. Find the stream function and the streamlines at t is equal to. And the streamlines for this field at t equal to 2. Can I solve this? Yeah. Y plus t. V is anybody got the answer? Exactly the same procedure. Okay, so let me solve this. So this is nothing but Q is nothing but Ui plus Vj, or U is equal to minus x and V is equal to y plus t. So these are the velocity components, and then we know that, so exactly the same procedure. So that is U is equal to minus dou phi by dou x and V is equal to minus dou phi by dou y. And as per CR equations, dou phi by dou x can be equated to, so dou psi by dou y. So this is equation number 1, and this can be replaced with dou phi by dou y can be replaced with minus of dou psi by dou x. So this will be dou psi by dou x. So these are the two important relations that we can make use of. Then minus dou psi by dou y minus dou psi by dou y is equal to minus x. So this is the velocity component u. These two will cancel out. It implies dou psi is equal to x dou y. If you integrate on either sides, this is psi is equal to xy plus some random function of, so x comma t, because it is done the integration with respect to y. So this is psi is equal to xy plus f of x comma t. And then from the other relation, so dou psi by dou x is equated to v. So psi we know now. So dou psi by dou x is equal to, so derivative with respect to x, that is y plus dou f by dou x is equal to the y component y plus t. So this y and y will cancel out. It implies dou f by dou x is equal to some function of time t. So this is, if you integrate dou f equal to t into dou x, so integrate on either sides. So this will be f is equal to, so tx plus some random function of t. So I call this as g of t. So this is f. So if you equate the f here, psi is equal to xy plus xt plus g of t. So this is a stream function. Understood? Now the stream function. So this is actually a generic function. Now he asked us one specific case. At t is equal to 2, what are the streamlines? So at any instant of time t is equal to 2, this value will be. So this is a function of x comma y comma t. Now actually instead of t he has given as 2. So psi of x comma y comma 2 is equal to xy plus 2x plus g of 2. So g of 2 is a constant. So because this is a independent of every other variable except for time, and t is also fixed now to a constant value of 2, this will be a constant function. Now psi is nothing but psi is equal to xy plus 2x plus constant. So this is the streamlines equation at time t is equal to 2. Got it? So this is as if like x common y plus 2 plus c. So this is the rectangular hyperbola equation. Clear? Any questions? Try to imagine the shape of this curve, how it is going to be. It's not 2x, so x taken out. So this is x is coming out here, y plus 2. So what is the shape of this curve? Where is the confusion? There is no confusion in this entire analysis. Right? So do you have any questions on this? If you don't have any questions, I am asking you what is the shape of these curves. So these curves are nothing but the flow directions. So because this is the stream function, right? So what are the shape of this? How it is going to be? Okay, so let me analyze this. See this. So let I call as z-axis represents the stream function. Then how the stream is flowing is on the right side. Now z minus c is equal to x into y plus 2. So it is nothing but the xy coordinate system. If you take this xy coordinate system, the origin is shifted to z equal to c, and then y equal to minus 2. So let us say this I call as the y-axis. Then on the minus 2 part, so y is equal to minus 2 and x is equal to 0 and z is equal to plus c. So this is the place of origin. So here, somewhere here on the x-axis, it is exactly at 0. Now at this place, if you cut the plane like a horizontal plane like this plane represents on top of this origin plane. So this is nothing but the xy plane at z is equal to c. Now there actually, if you notice, the xy relation will be the product of x into y plus 2 is equal to constant because z is fixed now, right? So at any random value of z, so it will be a rectangular hyperbola like this. But that rectangular hyperbola is shifted to x is equal to 0 and y is equal to minus 2. So this is nothing but just shifting the coordinate axis to a different location and trying to imagine the shapes there. This is what we call as the transformations in case of coordinate geometry, right? So these shapes are, so on the xy plane, if you notice, this is x and y. So this is y equal to minus 2 is this location. Y is equal to minus 2 is this axis. From here, what is happening is, these are the kind of shapes what you are going to get it. So these are the rectangular hyperbola lines. But these rectangular hyperbola lines are located at z is equal to c. So if you look at from the top, you are going to see the rectangular hyperbola shapes from the top if you see. But any instant of z, it will be exactly the same thing. It is matching one on top of the other, the same planes. Clear? Got it or not? Just try to imagine this way. Suppose there is a wall like this and there is a heavy fluid that is coming in this way. Then this wall will divert this flow in this manner. Got it? So this is the kind of shapes. If you look at from the top by standing on this wall, if you look at, this is the kind of flow you are going to see there, right? And this is the kind of shape what you are getting here. Any questions, Samreen? Okay. Now, coming to the concept of source. So here, the source is nothing but, you can imagine, so this is an abstract concept. So in reality, it may not be there. Here, there are two different kinds of sources. The source is nothing but, there is a place where the water is continuously produced from there. And this place is called as the source. So a source a place where the fluid is continuously generated. It's called a source. And a sink is nothing but a place where the fluid is continuously vanished out. So this is what is called as a sink. Now here, suppose, imagine that there is one place where the water is coming out of the ground. Let us say you are looking at the ground, and on the ground actually the water is continuously coming out from there. Now this water is continuously distributed across the surroundings there, right? And that place we call as the source. So the water will be going in all the directions like this. So from this is the source, the water is coming out. So this is what we call as the source. Suppose if the water is completely vanished out, so it has to attract water from all the directions. So here the water is going in. So this is the sink, right? So usually three-dimensional sinks are three-dimensional sources, and two-dimensional sinks and two-dimensional sources will be there. But in our syllabus we have only two-dimensional. So this is nothing but the water is continuously produced and then surroundingly distributed in a plane. So this is as if like it is a circle. If you draw a circle like this, so the water that is getting produced here is traveling in a planar direction in all the ways. Three-dimensional source is nothing but, imagine that in the middle of the water there is a generation of water, then the flow will go in all the three different directions. So that is the three-dimensional source. But for us we have only the two-dimensional source. Exactly the similar manner, this is a two-dimensional sink, right? So this is 2D only. Now in this case, so here actually how much quantity is getting produced there, that's what is nothing but the strength of the source there. Got it? So that means if you randomly draw a circle, the mass of the fluid that is getting generated at this point is nothing but the source strength. Yeah. Got it? Okay. So the mass of the fluid that is getting generated per unit time is nothing but the strength of the source, right? Or the volume of the fluid that is getting generated per unit time is nothing but the strength of the source, right? So here, suppose if the density, so let the density of the fluid be rho. So density of the fluid is rho. Now the mass of the fluid generated of a strength of or from a source of strength plus m. So this is usually represented with a letter called m. Source is with plus m and sink with minus m. So sink is usually represented with minus m, right? So the source strength is plus m. Then, so the mass of the fluid that is getting generated is defined as pi into rho into m. So this is the mass of the fluid that is getting generated. 2 pi into rho into m. This is, so initially when we wanted to find out the strength of the source, what we have defined is the mass of the fluid that is getting generated and crossing a radius of 1 meter is defined as 1 unit of the strength. Got it or not? So that means 2 pi into rho. Rho is the density component. M is the strength of the source. And then 2 pi into 1. 1 is the 1 meter. That means suppose if the fluid is getting generated and then to identify the strength of the mass, initially the way it was defined was, so by taking 1 meter radius, we counted within 1 second how much of the fluid is crossing this 1 meter radius. This is what is defined as the 1 unit of the strength. So that strength is nothing but 2 pi into 1 into m. So this, if you multiply it with rho, then this will become the mass of the fluid. Got it? So this is how it is defined. Now the same fluid, if you draw one more radius like this, then obviously the same fluid has to cross this outer radius as well, right? That is nothing but 2 pi into r into rho into, yeah, so 2 pi into r into rho. So this is the mass of the fluid that is getting crossed. Then from these two relations, rho and rho will cancel, 2 pi will cancel, right? Yeah. Just a minute. Yeah. Sorry. So if the velocity of the fluid that is getting crossed is qr, then the mass of the fluid that is getting crossed will be multiplied with qr, right? So qr is nothing but the velocity of the fluid in the radial direction, where qr is the velocity of the fluid in the radial direction. Got it? So here from this what you can get it is m is equal to qr into r. Or it implies qr is equal to m by r. Note down till this point. The mass that is getting generated, see this. Here the strength of the source is defined with m. So the definition of m is the mass of the volume of the fluid that is getting generated from a location that is crossing 1 meter radius. That means suppose I have drawn 1 meter radius here. Then the strength of the source is m here. Now how I can define the strength of the source? What I have done is I have taken a clock and then I tried counting it, and then the mass is getting generated here. The same fluid is crossing this radius in all the directions, right? So in all the directions the fluid is crossing. how much volume this is crossing in 1 unit time is nothing but the amount of volume that is getting generated by this source. Correct or not? Understood, Rishi? So this is what is defined as one unit of the strength of this particular source, and that we can get it, that is 2 pi into 1 into, so this is 2 pi is nothing but the amount of volume that is getting crossed here, right? So that is, so 2 pi into rho into m is nothing but the total mass of the fluid that is getting crossed this. So if m is the strength of the mass, then for unit strength this is 2 pi. For m strength this is 2 pi m. Got it? If you multiply with rho, then you are going to get the mass. So 2 pi m is nothing but the volume. Multiply with rho, you are going to get the, so you are going to get the mass of the fluid that is crossing this. Now, suppose if this fluid is crossing with a velocity of qr in the radial direction, this is qr, then at any random instant of radius r, so this value you want to count it. So at this radius of r, it is crossing with a velocity of qr. Then the mass of the fluid that is crossing this outer radius, I just wanted to find out the strength of this. So this strength is continuously producing. I wanted to find out the velocity of the fluid at this location. This is a different location than initially what we found at 1 meter, right? So this is based on the understanding of the source strength. But practically what we are going to deal with at any random radius of r. So here the amount of fluid crossing this outer radius will be 2 pi r times of qr is the volume that is crossing, and multiply with rho, you are going to get the mass of the fluid that is crossing the outermost radius. And the same mass is getting generated by a strength of source m. So 2 pi rho m should be equal to 2 pi r into rho into qr. Is this understood now? Right? So from this relation, what you have got is the radial velocity qr is nothing but m by r. That's it. Understood? Any questions? Fine? Okay. So from this understanding, what we have got is the radial velocity is nothing but qr is equal to m by r. So this is the source and this is the radial velocity qr. Then this can be divided into horizontal component is qrx is equal to m by r cos theta, and the vertical component will be m by r sin theta. So this is the velocity direction in the x and this is the velocity direction in the y. So we have got the horizontal component of velocity and the vertical component of velocity if you want it in the Cartesian coordinates. Now this qr is nothing but m by r. So the velocity, radial velocity in polar coordinates. So q is equal to, so this you are going to get it minus dou phi by dou r is nothing but the radial velocity in the radial direction. So this is the velocity potential phi. So this is a scalar potential in polar form. So this is in polar form, right? So minus dou phi by dou r, and the same thing is equated to minus of 1 by r into dou phi by dou r is nothing but dou psi by dou theta. So this is the CR equations based on CR equations. These CR equations I have derived yesterday for polar. Now from this QR actually I got as m by r, and this is nothing but minus of dou phi by dou r. So if you try to do the integration and find out the phi value, dou phi is equal to minus of m by r into dou r. Now, if you integrate it on either sides, then phi will be minus m into log r. Got it? So minus m log r is nothing but the velocity potential in the polar form. And similarly, if you equate this minus m by r is equal to minus of 1 by r into dou psi by dou theta. So this r will cancel. Yeah, this is correct. So r will cancel. Then minus dou psi is equal to m dou theta. And then if you integrate on either sides, psi is equal to minus m theta. So this is the stream function. This is the stream function. This is the velocity potential. For a source. Got it? So if your source of strength m is given, the potential function will be minus m log r and the stream function is minus m theta. Got it? Noted down? Got it? So finally, in the complete analysis, if you notice, we are doing only very few things. That is, trying to find out the potential function, trying to find out the stream function. These are the two important aspects. That's what we are going to do here. Now, for the comfortability, what we are doing is these things we are relating to the velocity. So, velocity, potential function, stream function. These are the only three important aspects. That's what we are going to do it in the complete fluid flow. Got it? But different scenarios. Done. Now we are going to find out the complex potential. So this is in polar form. The same thing we can even write in the Cartesian form. So in the Cartesian form, so Q can be written as, so this R Q is equal to Ui plus Vj. Now Q is nothing but, there what we have got is m by r cos theta into I plus m by r sin theta into j. Right? So m by r cos theta into I, m by r sin theta into j. So where u is equal to, so this is u and this is v. Right? So the complex potential function, what you are going to get it is dw by dz is nothing but minus u plus iv, right? Minus u plus iv. So it implies minus u is nothing but minus of m by r into cos theta plus minus of m by r into sin theta into I. So this is minus m by r. If you take it out, then this will be cos theta plus I sin theta. Got it? Cos theta plus I sin theta. Now this can be written as, by Euler's theorem, minus m by r into e power I theta. So this is dw by dz. Sorry, this is plus. Then this will be minus and this will be minus. So this is dw by dz is equal to minus m by r into e power I theta. So this is minus m by z, where z is equal to e power r e power I theta, or dw is equal to minus m into dz divided by z. If you integrate on either sides, it will be w is equal to minus m log z. And this is what we call as the complex potential. Of a source. So this is one of the very important thing what you need to remember. Minus m log z. Yeah, Anjali, you are correct. Yeah, so I have corrected. Fine. So this is source of strength. So if there is a source, then minus m log z is the complex potential. Now if you divide this complex potential into real and imaginary parts, then that will become the complex potential. So that will become the scalar potential and the stream function, right? So you are going to get it separately if you divide it into the real and imaginary parts. So straight away, if there is a source, then you can replace the complex potential there as minus m log z. If there is a sink, then minus m will become plus m. That is the difference. So for a sink, W sink is nothing but m log z. This is the complex potential of a sink which is located at z. Z is equal to 0. Now, if you want to shift the location of the sink or the source, suppose at this location, that is at origin, if the source is located, then the complex potential is minus m log z. But the same is located at this point, let us say z1, then this will be minus m log z minus z1 is the complex potential for a source which is present at z is equal to z1. Clear? So any questions? This is very important. You have to memorize this because multiple locations we are going to use this, and based on this only many questions came previously. So with this, I would like to stop the class for today. In the next class, I am going to deal with the doublet. So doublet is nothing but a source and sink together always comes together. Last up here, see this. I hope you understood till this point. W is equal to minus m log z is nothing but the complex potential of a source which is present at z is equal to 0. Now, same thing, this source, if I place at this location rather than here, that means there is a shift of coordinate axis from here to here. So to a location of z is equal to z1 in the complex plane. So that is nothing but the complex potential will become for a source which is present at z is equal to z1 with reference to the coordinate axis at this location as the origin. So from this point it is at z1. Hence the complex potential will be minus m log z will become z minus z1. Z will become z minus z1. Z is a variable. Z1 is a constant, complex constant. Z minus z1. It is as if like, suppose if I have a point at x is equal to 4. So this is nothing but shifting the coordinate axis from x to x minus 4. Then the origin will become x is equal to 4 for us. Got it or not, Liju? So basically you are replacing z with z minus z1. That's it. So if it is the sink, then it will become the sink of strength m, then it will be plus m into log of z minus z1 is nothing but the source potential. So is nothing but the sink which is present at a location of z1. The complex potential will be m log z minus z1. Fine. So with this, I would like to stop the class for today. In the next class, I am going to deal with the doublet. Okay. Yeah. So thank you. Yeah. Good morning. Bye bye.